Alright, so moving on from graphing, we're not really moving on, we're just continuing on. Got a lot more to do about graphing. So we skipped Unit 4, we just finished up Unit 3, we're going to skip Unit 4, and we're now in Unit 5. So we actually skipped all the way to Module 11. So this is 11.1. Looking at solving systems by graphing. Alright, this is a bunch of vocabulary on this board already, so you're just going to have to pause it and go ahead and write these down before we go on, because I'm going to have to erase it to do the practice problems. So make sure you get all this down before we continue on. Okay, so system of linear equations. So two or more linear equations, so linear meaning straight, remember, with the same variables. So all of ours are going to be using x and y because that's what we're used to. Okay. Solution of linear system, so an ordered pair that satisfies or is true for all of the equations in the system. So remember, an ordered pair is an x comma y ordered pair. Okay. Consistent system, a system with at least one solution. So there might be one solution, there might be two solutions, three solutions, four solutions, or more. At least one. It cannot be zero. Inconsistent system is a system with no solutions at all. Okay? Independent system is a system with exactly one solution. Exactly, so it can't be two, can't be zero, it has to be exactly one. And a dependent system is a system with infinitely many solutions. Meaning that every solution is shared. Okay. So I'm going to erase this whole thing now. If you need to, just pause the video, get it written down, because I do need the board to do our practice problems. Okay, so a system of equations, it sounds pretty complex. It's actually very simple to what we were just working with. So if you look at your definition for a system, it says that it has at least two linear equations. Before we even look at two linear equations, we're going to just do a brief reminder of one linear equation. So we know with linear that it's a constant rate of change, a constant slope, and that it would look like on a graph a straight line. Okay, so if I drew the graph, I'm going to put it in y equals mx plus b form to make it easier for us. So 3x minus 2. Our slope is 3, and our y-intercept is negative 2. And if I go to graph that, my y-intercept is negative 2. And my slope is up 1, 2, 3 over 1. Up 1, 2, 3 over 1. Or I could go down 3, back 1. That all should get me the same line. So with this linear equation, any point that I choose on the line, this point right here, which is 0, negative 2, or this point right here, which is negative 1, negative 5, or this point here, which is 1, 1, or this point here, which is 2, 4. All of those points are solutions. Are solutions to this equation. Okay? But in this situation, we only have one linear equation graphed. And in order to be a system, we have to have at least two. So if I were to add in another line, let's say y equals negative 3x plus 1, where the slope is negative 3 and the y-intercept is positive 1. If I were to graph that, I would start at my y-intercept of 1, and I would go negative 3, 1, 2, 3 over 1. Negative 3, 1, 2, 3 over 1. up 3, back 1. Okay, and I'd get my line. Alright, so what I have here is I have a system of equations. I have at least 2 linear equations. And if we look on this graph here, some of my solutions of this graph are -1, 4, that point there. This point is 0, 1. This point is 1, -2, etc. Okay? So we are looking to see what solutions do these two share. I'll write that down because I think that's important to kind of realize the question that we need to ask ourselves. What solutions do these linear equations share? Remember, when we talk about solutions, we're talking about ordered pairs. So what ordered pairs do they share? I'm just going to give you a brief little hint. This is going to be our solution, right where they cross, right where they meet. That is the solution they share. That point right there, right where they cross. Okay, so I'm going to erase this. If you need it, just pause the video. And I'm going to ask you to do 2 things for me right now before we move on the left-hand side. What I want you to do is, for this graph, I would like you to graph it, and then I want you to tell me or identify 2 solutions. And I'm going to challenge you to also think of 2 non-solutions, just meaning that they're any ordered pair that is not a solution. So I want you to tell me 2 solutions and 2 non-solutions of that line there. Alright, that's on the left-hand side. Please pause your video, do that now. Okay, so moving back to thinking about systems and solutions of systems, I'm going to give you guys 4 examples here. Just 3 examples. Each one of these is going to be a system of equations. So the first one, I'm going to have 2 linear equations. And we're going to think about how many solutions those linear equations have. Here I'm also going to have 2 linear equations and thinking about what solutions they have. And here as well, I'm going to have 2 linear equations thinking about what solutions they have. So if we look at the very first one and we think about the solutions of this very first system of equations, the solution is a point that is a solution for both lines. So if we were to say, well, maybe this point right here is a solution of this system. No, it's not, because it doesn't lie on the purple line. It has to lie on both lines to be a solution. It has to be a solution of both of these. So what about if we picked a point out here? That doesn't work because it has to be a solution of both of these. So we have to pick the point that they both share, which is that point right there. And so there is only one solution here, one point that these 2 linear equations share. One solution. Okay. If we look at this one over here, and we think about, well, let's pick this point here. That point is not a solution of either linear equation, so that doesn't even work. That's a non-solution of both equations. If we picked one here, that's a solution of the purple, but not of the blue. We need it to be a solution of both. If we try this one here, that's only a solution of blue, not of purple. That doesn't work. This one, since they are parallel, remember they are going in the same direction, parallel, that means that they have the same slope, right? The same slope, and they have no solutions. They never cross each other. There's no point. There's no point that we could pick that's true for the purple and the blue. There is no such point. So no solutions. Right? The very last one if we pick a point out here, that does not work. That is a non-solution of both linear equations. So we have to pick a point. Let's try this point here. That point is on both the blue line and the purple line. It's a solution of both equations. So that's a solution. What about here? That lies on the blue line and the purple line, solution of both. What about here? That's on the blue and the purple. Even though the blue line stops here, there's an arrow that tells us that it goes on forever. So it lies on both lines, this one, this one, this one. It turns out that every single point on this line, they share, right? They share every point. So this is what we call infinitely many solutions. That means that they share every single ordered point. And if you look at them, you can tell that they are the exact same line. They have the same slope, and they have the same y-intercept. All right. So this is just a visual to help you out in identifying if there's one solution, no solution, or infinitely many solutions. So I'm going to erase this, and I'm going to give you guys some practice problems now. Okay. So I'm going to give you about 4 or 5 of these. I want you to identify whether there's one solution, no solution, or infinitely many solutions. I'm actually going to give you 6. So you're going to be drawing these on the left-hand side, draw them out, and identify whether there is one solution, no solutions, or infinitely many solutions. Assume that if they look straight side to side or up and down, or if they look parallel, assume that they are. Of course, I'm drawing here, so things are not going to be perfect. Okay, one solution, infinitely many solutions, or no solutions for all of these. You should be drawing them out as well. Okay, so pause the video, get these done on the left-hand side. One solution, no solution, infinitely many. Alright, so you're back with me now. I'm assuming you've already completed these on the left. I will not tell you the answers for these. Okay? We're actually going to start solving some now, actually getting our solution. Okay, and all we're doing, there's lots of ways to solve them, but we're going to be solving by graphing the entire time. So we have our 2 equations, right? Because we need at least 2 equations in order for it to be a system. Our first equation is 2x plus y equals 6. And our second equation is negative x plus y equals 3. Since we are graphing, I'm going to ask that we do the same thing that we've done before in getting our equation in slope-intercept form. So that means that we need to get the y by itself. Neither case is the y by itself. So in number 1, we have 2x plus y equals 6. In order to get the y by itself, we need to subtract the 2x from both sides. And we get y is equal to, we cannot combine those, do not go together, but we'd like to list the x first. So we get negative 2x plus 6. Okay. The next one, we get negative x plus y is equal to 3. We want the y by itself, which means that we are going to add the x to both sides. The 3 and the x are not like terms, so they cannot be combined together. We get y is equal to, the x is listed first, x plus 3. Okay, we're going to go ahead and graph these out. So number 1, we have a slope of negative 2 over 1 and a y-intercept of 6. Okay, so our y-intercept is 6. And our slope is negative 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. And we got our line. graph the blue one next. That's our number 2 equation. And it has a y-intercept of 3 and a slope of 1 over 1. So a y-intercept of 3 and a slope of 1 over 1, 1 over 1, 1 over 1, down 1, back 1, etc. So with these two lines here, you can tell that they cross in one spot, so they have one solution, and the solution is where they cross, where they meet, which is right there. Okay, so that coordinate point, that solution, is at 1, 4. 1, 4. So we just solved that. That was it. That's all we needed to do. There's our solution. That's all we were trying to identify. But I do want to show you guys why it works. I do want to show you how we know that this is a solution. So if I take this point, my x value is 1, my y value is 4, and I'm going to look at it in both of these equations. Actually, I'm going to erase all this work here. I'm going to use the original equations that we had. So for the first one, I get 2 Okay, we're going to plug in what we know. We know that our x value is 1 and our y value is 4. 2 times 1 is 2 plus 4 equals 6. 6 equals 6. So far we are good for the first equation. Okay, for the next one, we have negative x plus y equals 3. We plug in what we know. We know that the x is 1 and we know that the y is 4. So we get negative 1 plus 4 equals 3. For me, I like to read this in the opposite order. I'm just going to switch them. 4 minus 1 is equal to 3. So 3 is equal to 3. We got it. Okay, that is why it works. It works for these equations. It works for these equations. That's why that point is the solution. If we were to pick another point, it wouldn't work when we plugged it in. So let's say I pick the point 0, 0. Okay, the point 0, 0 right here is not a solution for either line. So if I pick the point 0, 0, it should not work. So for number 1, we get 2. Remember, I'm plugging in 0 for both variables. 2 times 0 is 0. 0 does not equal 6. That doesn't work. Okay, let's try the next one. It should not be a solution of either of these. Negative 0 plus 0 equals 3. 0 plus 0 equals 3. 0 equals 3. It does not equal 3. That does not work. So those are both no good, and that's what it shows in our graph. That is not a solution of either equation. Okay. I was going to show you guys another example, but I'm just going to have you guys practice one actually. Okay. So, the one I want you to practice, doing this exact same process. Y is equal to 2x minus 2. That's your first equation. Remember, we need at least 2 to be a system. So our second equation is 3y plus 6x is equal to 18. Okay? And the question is asking you, what is the solution of this system? Solution. So that means that your answer should look like an x, y coordinate pair. Okay. I will say, so if you want to pause the video now and try it out, go ahead. I will say, though, that I do not want this to mess you up because this is a previous skill that you should already have. So when you get the y by itself here, this is what it should look like. Negative 2x plus 6. If you don't get that, this is the equation you need to use. Okay, that's the equation you need to use. You should be able to do that, but if not, go ahead and just jump to this equation. All right, pause the video now, graph these, and give me a solution. Okay, so you're back with me. I'm assuming you've already done this. You've gotten a solution out of it. No, I'm not going to. I'm going to do two more, but they will be a little bit different. All right. Y equals 2x minus 2. That's just a line. It's not a system yet. We need at least 2 to make it a system. 3y, 6x is equal to 18. Awesome. All right. Just kidding. Just kidding. Don't write that down. Don't write that down. Oh, sorry. Negative 2x plus y equals 4. Beautiful. Here's our two equations. We are going to solve them. We are going to get our solution out of them. So in order to graph them, because that's what we do is we graph, we are going to need to get the y by itself. In number 1, it's already done. It's in slope-intercept form. Number 2, it's not. So negative 2x plus y equals 4. We're trying to get the y by itself for slope-intercept form, so we add 2x to both sides. The 4 and the 2x are not like terms. We cannot combine them, so we keep them separate, but we're going to list the x first. So 2x plus 4. Now we have our slope is 2, and our y-intercept is 4. Cool. All right, so we're going to graph these guys. Do you guys ever need graph paper during this? Just get up and get some. You don't need to ask me, just get up and get some. Alright, the first one. Our slope is 2 over 1, and our y-intercept is negative 2. We started our y-intercept with negative 2. We go up 2 over 1, up 2 over 1, up 2 over 1, and we've got our line. Down 2, back 1, etc. Cool, there's our first line. Our next line has a slope of 2 and a y-intercept of 4. So we start with our y-intercept of 4, and then we use a slope of 2. I can't go up 2 over 1. Well, I could. It'd be a route right there. But instead, I can always go down 2, back 1. Down 2, back 1. Down 2, back 1. Alright, so we notice on this graph, it is not obvious that they're going to cross somewhere. Alright, we don't really see a point where they're going to cross. They actually look like they might be parallel. So if you go back in your notes to where we looked at the visual of these parallel lines, you'll remember that I said that these have the same slope. If they're parallel, they have the same slope. So let's look at this. Number 1 has a slope of 2. Number 2 has a slope of 2. Guess what? They do have the same slope. So that means that they are parallel lines, which means that they have no solution. They do not cross anywhere. They do not share any points, so there is no solution. So when you were on a test answering this question, you would just write no solution. Awesome. Okay, one more from me, and then you guys will have 2 more practice problems, and you will be done. Okay. All right. Last. Okay. 2 equations. Y equals 3x minus 3. So far, it is just an equation. It's not a system yet. We need 2 equations to be a system. So our next line, so that we can make it a system, is negative 3x plus y equals negative 3. All right. So we always want to get them in slope-intercept form because we are graphing. First one's in slope-intercept form. The second one is not. So we need to get the second one as y by itself. So we would add 3x to both sides. 3x and negative 3 are not like terms because there's no x here. So we get y is equal to, we do not combine those. I'm going to list the x first. 3x minus 3. Cool. They're both in slope-intercept form. We are going to graph them. So for the first equation, our slope is 3. Our y-intercept is negative 3. So our y-intercept is negative 3. And our slope is 3 over 1. So we go up 3, 1, 2, 3 over 1. Up 3, 1, 2, 3 over 1. Up 3, 1, 2, 3 over 1. Or down 3, 1, 2, 3, back 1. Good. And we've got a line here. Awesome. Our second equation has a y-intercept of negative 3 and a slope of 3 over 1. So we started our y-intercept of negative 3. And we use a slope of 3 over 1. 1, 2, 3 over 1. 1, 2, 3 over 1. 3 over 1. Down 3, back 1. And we get our line. This is weird. Looks like the equations lie right on top of each other. Okay? We did have an example like this previously, but I want to bring something to your attention. This equation and this equation, 3x minus 3. 3x minus 3. Same equation, same slope, same y-intercept. They turned out to be the exact same graph. Wonder why. So these have infinitely many solutions, just like we saw in the example. So if you were to get a question that asked you something like this, your answer would be infinitely many solutions. Alright, I have 2 practice problems for you, and then you are done with this lesson. I'm erasing this. If you still need it, pause the video. Okay, the question is going to be the exact same for these two. It's going to be asking you whether there's no solution, a solution, or infinitely many solutions. If there's a solution, give me the solution. So the first one, y equals negative x minus 2 and x plus y plus 2 equals 0. And the second one, y equals 2/3 x minus 1 and negative 2/3 x plus y equals 1. Right. So, if you have a hard time rearranging this one, just call me over because you need to know how to do that. You're just getting y by itself. It shouldn't be hard. Alright, you're graphing these, finding me the solution, and then you are done with this video. Remember, you will not be able to enter into class tomorrow if you have not finished the left-hand side, so make sure you get these done. Alright.